Hi, I'm Randy Becker, an applications engineer at Agilent Technologies. I have with me Martha Zametti, also an applications engineer at Agilent. We're going to give you a quick overview of Agilent's test solutions for LTE-Advanced carrier aggregation.
So let me start with a brief explanation of what carrier aggregation is. Carrier aggregation is defined in Release 10 of the 3GPP standard, and it simply means combining two or more LTE carriers in order to have a wider transmission bandwidth. And these carriers can either be allocated contiguous to each other in the same band, or they can be non-contiguous in the same band or in separate bands. Even though you can aggregate up to 5 carriers, today the industry is focused on a maximum of 2 component carriers, with most of the interest being in the downlink interband configuration, where the carriers are in separate bands. What does this mean for operators? It means they can utilize the fragmented spectrum that they own in order to achieve a much higher downlink data throughput. Carrier aggregation also allows interference mitigation in a heterogeneous network by using what's known as across-carrier scheduling. Now I'm going to have Randy tell us more about what the test challenges are.
From the base station perspective, we have multiple component carriers that are being transmitted, and each one of these must maintain strict RF requirements in terms of ACLR, EVM, and spectral emissions. Additionally, each of these component carriers must maintain strict RF timing alignment with respect to each other. One of the test challenges is being able to simultaneously measure these component carriers, which can have frequency separations wider than the bandwidth of a single analysis instrument. From the mobile perspective, we need to be able to receive multiple component carriers, typically at very low power levels and often in the presence of a high power blocker. Additionally, each of these component carriers could be received by a separate antenna and RF subsystem, increasing the possibility for intermodulation distortion, crosstalk, and other self-blocking issues. To troubleshoot and measure system performance, we need to be able to generate laboratory-grade LTE-Advanced carrier aggregation signals. Now let's take a look at our demo setup. On the bottom I have 2 X-series signal generators, and on the top I have 2 X-series signal analyzers. The reason we have 2 pairs of instruments is we're simulating the situation where we would have one set of carriers at a very low frequency, say from this pair of instruments, and a set of component carriers at a higher frequency. Often these can be separated by more than 1 gigahertz. We have a laptop here which is running our Signal Studio software. This will generate and create the LTE-Advanced signal, which is downloaded into the signal generator. We also have the VSA software, which synchronizes the signal analyzers and acquires the data for simultaneous demodulation, which is important. So now let's take a look at the Signal Studio software and see about generating the LTE signals. In the software configuration, you can see that I have a downlink Release 10 configuration with 2 component carriers. Each one has been assigned to a different signal generator that can be tuned to any frequency and amplitude to simulate 2 different bands. By clicking on the Add CC button, or Add Component Carrier button, I can add additional component carriers to either band. So this is ready for future scenarios that a designer might want to investigate. Now we'll look at one of the data channels on one of the component carriers. First, you can see at the bottom of the screen the resource block allocation graph that gives a visual of our current configuration. As a quick note, the light blue lines are the reference signals, while the red areas are the PDSDH, or downlink data channels. Notice that I can select from any of the different transmission mode types. Since I only have 2 signal generators, one for each band, I am limited to SISO configurations. But we can configure each of the component carriers for up to 8x8 MIMO with additional signal generators. Next you will see I have access to the cross-carrier scheduling. Here I can configure whether or not a particular user should use cross-carrier scheduling, and which component carrier should be used to get the downlink resource block allocations contained in the PDCCH, or control channel. Of course, the user has full control of all the other parameters like power level, resource block allocation, RNTI type, and cell ID. But we looked at some of the things that were new for carrier aggregation in Release 10. Once we're satisfied with the configuration, we will simply download the signal to the signal generators, and we would feed that signal into our device under test to see how well it can demodulate that signal. Now that we've generated the signal, let's take a look at the analysis.
I've set up the VSA software to automatically detect the configuration of each carrier from the two X-series signal analyzers. On the bottom two screens, you can quickly see the spectrum of each carrier. In the top two windows, we can see the constellation of each carrier, along with color-coded list of all active channels and their individual EVM. The last two windows, we can see the error summary for each carrier with composite EVM, frequency error, timing offset, and a lot more error metrics. This is just a small fraction of the data that can be displayed. Let me add two additional traces to show the EVM as a function of subcarrier or a function of time, which is very useful for troubleshooting. For example, if there was an issue with the EVM, you could determine if it was happening only in selected time instances and identify which subcarriers were at fault. A very powerful feature for troubleshooting is marker coupling. It's very helpful in relating error results displayed in different domains, such as the constellation diagram and the various EVM traces as shown here. The marker table on the bottom returns all the marker values, which is helpful in pinpointing which channel, subcarrier, or symbol has the highest EVM. As you can see, there is quite a list of data that can be displayed depending on the type of analysis you need to do. Also, by pressing this red button, I can store the digitized data to the hard drive of the analyzer so I can refer to it at a later time or even share it with colleagues in another location. That completes a quick tour of the LTE-Advanced carrier aggregation analysis.
We just showed you how to generate and analyze LTE-Advanced carrier aggregation signals with wide frequency separation using the X-series instruments.
If you'd like a free trial version of either the Signal Studio software or the VSA analysis software, please see the URL shown on the screen.
Thanks for watching.